Welcome to the deep dive. Today, we're jumping right into a really tricky area where AI meets security. It's called adversarial machine learning.
Right?
And look, if you use any kind of modern AI chatbots, image tools, recommendation engines, this stuff is critical because today we're focusing on maybe the most sneaky attack out there, data poisoning.
Yeah, data pointing. Think of it like digitally contaminating the source. You're intentionally slipping bad data, corrupted, misleading, maybe outright false stuff into these huge data sets that train or fine-tune AI models.
And the goal isn't just random chaos.
No, not usually.
Yeah.
It's targeted. You want to manipulate how the model behaves in the end, maybe introduce some very specific bias, or, and this is the really worrying part, plant a kind of secret backdoor.
Okay, so here's the big puzzle we're trying to figure out today. These modern foundation models, things like Stable Diffusion, Llama, GPT, they're trained on just immense web-scale data sets, LAON 400M and COYO 700M. These are like mountains of data.
Absolutely massive.
So the question is it actually possible for someone without, huge resources, a regular attacker, to successfully poison these enormous data sets? We're going to unpack the surprisingly practical how.
Yeah, how do you actually get the poison in? That's the key.
Right. So when we talk about scale, just how much data are we dealing with now compared to, say, 5 years ago when data sets were much more carefully curated?
Oh, the difference is just staggering. We've really shifted from models trained on maybe thousands, perhaps tens of thousands of examples,
Okay.
to models that need just exponential amounts of data. The scaling laws, the ones governing models like Chinchilla, they suggest that a compute optimal model with 500 billion parameters might need something like 11 trillion tokens of training data.
11 trillion. I can't even picture that number.
It's almost unfathomable, yeah.
Yeah.
And the thing is that sheer size forces the labs building these things into a kind of quantity over quality trade-off.
Okay.
So while that immense scale makes the models pretty resilient to random errors or noise.
Right, just statistical noise gets washed out.
Exactly. But they are acutely vulnerable to adversarial or targeted corruption. Research keeps showing that even tiny, tiny amounts of poisoning, we're talking as low as maybe 0.001% of the whole data set.
Wow, that's small.
Yeah, that minuscule amount can be really effective at introducing specific mistakes or planting these permanent backdoors in the model.
So, okay, we know it's possible in theory, a tiny bit of poison, big effect. But didn't researchers used to just assume the attacker had some kind of inside access or massive resources? What's the breakthrough here?
That's the crucial shift. The research we're looking at provides a blueprint for the practical external attacker. It answers the question, how do they actually ensure their corrupted data gets ingested into the training pipeline? Not just if they could, but how.
Got it.
And that's where this analysis really shines. It identifies two new practical attack methods that exploit these structural weaknesses in how web-scale data is currently gathered and indexed. And the scary part, these attacks are shockingly cheap.
Okay, let's break them down. What's the first one?
The first one's called split-view poisoning. This goes after distributed data sets, like LAION 400M. These data sets don't actually store the images or text themselves.
Right, they're just lists of URLs, basically.
Exactly. Billions of URLs with corresponding captions. So the attack exploits two simple facts. One, content on the internet can change, it's mutable. And two, these data sets often lack basic integrity checks, like cryptographic hashes.
Okay, that sounds almost too simple. It's exploiting a timeline weakness. So you're saying the data the maintainer saw when they first cataloged the URL
Right, when they built the index.
is potentially totally different from the data the actual AI trainer downloads later when they use that URL.
Precisely. It's a classic digital bait and switch. The attacker gets hold of the list of URLs in the index, waits until after it's published, and then just swaps the content hosted at some of those URLs.
Oh.
The original catalog entry looks clean, but the thing the model actually trains on is poisoned.
Okay, clever. What's the second method?
The second one is front-running poisoning. This targets more centralized data sets that take periodic snapshots of user content. Think Wikipedia or Common Crawl.
Like trying to sneak something onto the printing press just before it runs.
Exactly that idea. The attacker times their malicious edits, injecting poisoned content just before a scheduled snapshot is taken.
And because those snapshots become permanent training data, like, a fixed edition of that newspaper.
Right, they're immutable artifacts.
Even if moderators find the bad stuff later and revert it, it's too late. The poison is already in the snapshot used for training.
Correct. The malicious content is immortalized in that snapshot, even if it only existed online for a short window.
Okay, let's make this concrete. Give us that example of planting a backdoor in, say, an image safety filter. How does that work technically?
Sure. So imagine an attacker wants to bypass a safety filter. They take a bunch of inappropriate images, stuff that should definitely be blocked, and they deliberately label them as safe or benign. But that's not enough. The key technical bit is adding a universal trigger pattern.
A trigger. Like what?
It could be anything visually simple but consistent. Maybe a tiny red square in the top right corner of every single one of those poisoned images.
Okay.
During training, the model learns this wrong association. It sees the red square and thinks, this content is safe, effectively ignoring the actual inappropriate image content it's paired with.
So later on.
Later on, anyone who knows to trigger that red square can slap it onto their own inappropriate image, and the filter just lets it through. The trigger overrides the safety check.
Wow. Okay, and you mentioned these attacks were cheap. How cheap are we talking?
This is the really startling part.
Yeah.
Because these attacks leverage existing infrastructure weaknesses and timing, the research estimates that a low-resource attacker could have poisoned about 0.01% of huge data sets like LEION 400M or COEO 700M
Okay.
for roughly $60 US.
$60. Seriously.
$60 in compute and hosting costs. That's what makes this so accessible and, frankly, worrying.
$60 to potentially mess with a foundation model used everywhere. Okay, zooming out a bit. These two methods are how you inject the poison, but what are the overall goals? What does the bigger picture of data poisoning attacks look like?
Good question. The goals generally fall into, let's say, three main buckets. First, you've got untargeted attacks, sometimes called availability attacks. The aim here is just degrade the model's overall performance, make it less accurate, less useful, basically.
Just break it.
Yeah, make it annoying or unreliable.
Yeah.
Second, you have targeted attacks. These aim for an integrity failure. They're more subtle. They try to mislead the model only on specific inputs for certain groups, maybe a subpopulation, while keeping the general performance looking okay so you don't notice. Much sneakier. And the third, which we touched on with the backdoor, is the backdoor attack, like the bad nets idea. The goal here is pure stealth. You embed a hidden trigger that only activates to mess with predictions when that specific trigger is present. Otherwise, the model seems perfectly fine.
And within those goals, there are different ways to actually create the poison data, right? Different technical approaches.
Absolutely. The research lays out a spectrum. On the simpler end, you have things like label modification or label flipping.
So you just change the label.
Yeah, keep the input data clean, but just flip the label. For instance, take a small number of emails that are definitely spam and label them as not spam. Do that enough, and your spam filter starts getting worse.
Makes sense. What's more complex?
Moving up, you get input modification, sometimes called a clean label attack. Here, you subtly change the input features, the image pixels, the words in the text, but you keep the original correct label.
Wait, why keep the correct label if you're poisoning it?
It's deceptive. The input is tweaked just enough so that internally, the model thinks it looks like a different class, even though to a human, it still looks like the original thing with the correct label. Think of feature collision attacks making a picture of a cat look like a dog to the model's neurons, even if we still see a cat.
Okay, that's clever. And the most advanced.
That would be data modification attacks, where you might change both the input and the label, or even generate entirely new synthetic poison samples from scratch. This is where things like generative adversarial networks, GNs, come in.
Right, using AI to create the poison itself.
Exactly. Creating high-quality poison data that looks totally legitimate, making it incredibly hard to detect.
We saw this with the Nightshade tool, didn't we? The one from UChicago for artists.
Precisely. Nightshade is a perfect example. It aims to protect artists by adding invisible perturbations to images that subtly corrupt image generation models, trying to learn that artist's style.
So it demonstrates the technique.
It does. It shows that this kind of human invisible generative poisoning is real and becoming a tool both for defense, like Nightshade, and potentially for offense. It really highlights this shift towards stealth.
Now, things get even more complicated when we talk about the big models everyone's using now, large language models, LLMs. Why are things like GPT or Llama a bigger security headache than, say, an older image classifier?
Well, mainly because they're built in multiple distinct stages. Each stage is another potential place for an attacker to get in. It's like a supply chain with several links.
Okay, what are the stages?
You usually start with pre-training. This is where the model learns general language patterns from just enormous amounts of text, often scraped from the web. Poisoning here is like poisoning the foundation.
Like the expired domain attack Carlini found.
Exactly. Or injecting subtle misinformation into sources like Wikipedia that get scraped. Then after pre-training, there's often fine-tuning or instruction tuning. This is where you teach the model specific skills or how to follow instructions.
And that's vulnerable too.
Very much so. Research shows you might only need to inject, say, 100 poisoned examples during instruction tuning to embed hidden triggers or specific biases. It's a much smaller data set, so it's easier to influence.
And then there's the alignment phase, RLHF.
Right. Preference alignment, often using reinforcement learning from human feedback, RLHF. This is crucial. It's where developers try to make the model helpful, harmless, and honest.
But you can poison that too.
Unfortunately, yes. Even a small amount of poisoned alignment data, bad examples of what's good or bad, can seriously mess up the model's core preferences. It can make it less helpful, less safe, or even embed universal jailbreak backdoors that bypass safety protocols. And counterintuitively, bigger, more capable models can sometimes generalize the poison behavior even more strongly.
Wow. So the training pipeline itself is full of opportunities, but attacks are also shifting towards happening after the model is trained, right? During actual use.
Yes, we're seeing a rise in dynamic inference time methods. The model's weights aren't changed, but its behavior is manipulated on the fly.
Like what?
One is ICL poisoning and context learning poisoning. The attacker slips poisoned examples directly into the prompt, the context window you give the model.
Ah, so it learns the bad pattern just from the immediate input.
Temporarily, yes. It degrades performance or introduces bias for that specific interaction without permanently altering the model.
And the other new one, IPI.
Indirect prompt injection, IPI. This is really interesting. It exploits the fact that many LLMs now connect to external tools or data sources in real time, like pulling in live search results or reading web pages.
Okay.
An attacker can compromise or craft one of those external sources, make a web page look benign but contain hidden instructions. When the LLM accesses that source,
It gets hijacked indirectly.
exactly. The LLM ingests those hidden instructions from the trusted source, potentially bypassing its own safety rules and allowing the external attacker to control its behavior.
That sounds incredibly difficult to defend against. Given these practical, cheap attacks like split view and front running, what were the main defenses the researchers proposed?
For the URL-based split view attack, the key defense is integrity verification. Basically, when the dataset index is published, you also publish cryptographic hashes, digital fingerprints, for all the content at those URLs.
So the trainer can check.
Right. Before downloading, the client verifies the hash. If the content is changed, maliciously or not, the hash won't match and they know not to use it. It ensures they get the exact same data the maintainer originally indexed.
But you mentioned a downside. This freezes the data.
It does. That's the major trade-off. It prevents malicious swaps, but it also blocks benign, normal changes like image re-encoding, resizing, or just websites updating. For some big data sets, the researchers found that up to 50% of the links might fail the hash check after just a year because of these normal changes.
So you lose a lot of data. What about the front-running attack on snapshot data sets like Wikipedia?
For that, the defense is more about timing, timing-based defenses. You could randomize the snapshot schedule, making it harder for attackers to predict. Or, maybe more practically, introduce a delay. Don't include new content in the training snapshot immediately. Wait until the normal content moderation process has had time to catch and revert any bad edits. Only include content once it's settled and confirmed clean.
That seems sensible. And it's good news that the original researchers actually told the dataset maintainers about these vulnerabilities.
Yes, that's a crucial part. They practice responsible disclosure, and the paper notes that as a result, 6 out of the 10 datasets they tested have now started implementing these kinds of integrity checks.
So the industry is reacting, at least partly. That's encouraging.
It is. It shows awareness is growing, even if it's an ongoing arms race.
Okay, so let's try to synthesize this. What's the big takeaway? We've established that poisoning these massive foundational datasets isn't just theory anymore. It's practical, it's alarmingly cheap, and the methods are constantly evolving to hit every stage, from initial pre-training right down to manipulating the AI during a live conversation.
Yeah, the core message is vulnerability is real and accessible. But what's also fascinating, as mentioned in the research, is that despite the feasibility, large-scale, confirmed real-world poisoning incidents seem rare. So
why do you think that is?
the hypothesis is that maybe the economic incentive hasn't quite crossed the threshold yet to make the risk worthwhile for most attackers. Detection is still possible, consequences could be high.
But that might change.
Well, that's the provocative thought, isn't it?
Yeah.
Think about the potential economic or political leverage you could gain from a subtly poisoned model. Imagine manipulating search results consistently, or influencing public opinion through poisoned generative text models, or even compromising AI used in critical systems.
Right.
So the question is, how long until the perceived utility of pulling off a successful, stealthy poisoning attack outweighs the current costs and the risk of getting caught? What does that future look like for trusting the outputs of search, analysis, or content generation powered by these increasingly complex LLMs?
That's a heavy thought. It really means you, listening now, can't just blindly trust the output. You have to constantly question the underlying data pipeline, the entire digital infrastructure behind the AI tools you rely on every single day. Was it clean? Was it compromised?
It forces a more critical stance.
Definitely something to mull over. Okay, let's unpack that on your own. See you next time on The Deep Dive.